Hi, ladies and gentlemen. My name is Dithoto Modungwa, and I'm from the Language Sciences Impact Area and within the Technical Mobility Research Group. And today I will be taking you through a presentation on one of the emerging and most trending topics, and that is of autonomous vehicles, and that will be in the context of South Africa. The presentation will cover an introduction and benefits of these kind of systems, the challenges that these present, levels of autonomy and off-road mobility and the complexities thereof. And lastly, we'll embark on I'll share about some of the work that we've undertaken that is related. Autonomous systems is quite a rapidly developing field of research, and with it presents numerous applications, and that's in various sectors ranging from transport, defense, social assistance, search and rescue missions, environmental monitoring, decision support, and also skills that are most applicable in smart factories or cities. And some of these benefits, now zooming into a social welfare point of view, include saving lives, reducing crashes on our roads. As we know, in South Africa, we have quite a high accident rate on the roads, traffic congestions, fuel consumption, pollution, and importantly, increasing mobility of elderly people and those that are physically impaired. The Technical Mobility Research Group based at Landwoods, we undertake work into autonomous mobile platforms which are geared towards removing the human out of danger as potential force multipliers, and also looking at vehicles of mobile platforms that could cater for both military and civilian applications. And part of our focus is also at localization, focusing on localization and or indigenizing of technology. And what that speaks to is adapting currently existing international systems to particular to our region, because it presents peculiar challenges thereof. And you don't always get systems that work perhaps in a European setting would work in South Africa or any other region. For example, there's been an initiative by Mercedes-Benz, which is called the Worldwide Test Drive, 5 continents and 5 months, and which looks at how autonomous systems or vehicles in particular are just in different regions. Also, part of the work that we do is the aim is also to foster capability development and collaboration, not just through postgraduate studies and tertiary institutions through the studentship programs offered by the CSIR, and also across impact areas and research groups within the CSIR. And the potential of that, which comes with these skills advancements, is that of creating spin-offs like SMMEs and so forth to support the industry that would come with autonomous systems, as far as within the manufacturing, maintenance, and services sector. Some of the challenges of autonomous vehicles within the South African context particularly is that many of our citizens rely on transport industry for jobs. And this would be taxi drivers, truck drivers, and bus drivers, and so forth. So, and we all know that autonomous vehicles or cars would lead to potentially a lot of retrenchments in that area. However, and that compounded with our current unemployment rate. However, some of these challenges could be addressed through reskilling. And when we touch on infrastructure that is necessary to support these self-driving vehicles or autonomous systems, which I'll use interchangeably throughout this presentation. For example, South Africa has approximately over 700,000 kilometers worth of road, and only over 160,000 kilometers worth of that component is paved, leaving much of it unmaintained, and also even in urban settings we have issues with potholes and lack of road markings and vandalized road signs, which are very key component to be able to navigate autonomously. So in order for the autonomous vehicles to be practical and safe, these are some of the infrastructure issues that would have to be addressed. And also there's the issue of the cost of autonomous vehicles. They come with specialized sensors, technology, and so forth, which is already we have vehicles are quite costly within South Africa. And that would be an added cost so part of what we do is how we become innovative in addressing some of these challenges. We have the peculiar road traffic challenges where we have different road surfaces, wildlife, and pedestrians, many pedestrians in both cities and interurban traffic moving around and crossing lanes completely unexpectedly and so forth. Incomplete road signs, and we have unique signs that speak specific to a country. We have issues with load shedding. How would we be able to back up and for the infrastructure that's necessary to support autonomous vehicles? Our policy and legislature would have to be amended. Just to introduce you on to what we call levels of autonomy. There's the South African, the Society for Autonomous Automotive Engineers is a professional association which often sets industry guidelines, and they went about in forming a classification system. There are various systems that apply, but we tend to use the Society of Automotive Engineers guidelines, and that speaks to the different levels of autonomy, and that speaks to the principle of shared control, because it's about the driver or occupant being a driver of the vehicle and how they share that with the autonomous system in the vehicle. And with that, you would have now, if you look at from a modeling and simulation point of view, you would have what we call an artificial intelligence system model and a driver model. And the different levels will speak to range from no automation at all, where it's the driver full on engaged with the vehicle and controlling the vehicle. And it goes from level 0, level 1, which there's driver assistance systems where, for example, things like adaptive cruise control. Level 2, which is partial autonomy, as you can see in the diagram there. The driver is still very much active and responsible, but there's things like adaptive cruise control. Level 2, which is where you have speed and steering in some situations. So the driver lets go off the steering wheel in some instances, and all the way to level 5, which is full autonomy, and that is, under all roadways and environmental conditions, there's no human intervention at all at that level. Now, as an example from the automotive sector, to draw on an example there, that speaks to development around this area and systems that have been developed to speak to the different levels of autonomy. There's the case study of Toyota, which has invested over $1 billion into the research and development to focus in development of robotics, automated driving technology, and authentication systems in vehicles. Now, an example of their systems, they have 3 systems. One, which is the first being the highway teammate, which takes control of the vehicle when driving on highways. And the second is the guardian mode, which simply monitors what the driver is doing, the tasks, and can help to prevent accidents. And I think this would be quite useful in South Africa, where we have studies have shown that a lot of road accidents are due to driver errors. And lastly, there's the chauffeur mode, which is a full autonomy mode, where the system is responsible for all driving tasks. I'd like to zoom in to what we call off-road autonomous mobility, which is quite a complex subject on its own, and which incorporates into it not just the normal systems that which of autonomy, which include object detection, perception, planning, classification, surface detection, environmental mapping, and so forth. But also now you take more specific interest into the environment, and that would include, when you talk off-road, it's unstructured environments. It's quite rugged in an environment. And further components of mobility would include vehicle-terrain interaction, and that's how the vehicle interacts with the type of terrain it's operating on. For example, we have deformable soils and so forth. That's the area you operate. You have rocky areas when you go off-road. And this is this is quite fitting for our case study of South Africa, because as mentioned earlier from the road situation. Now, when you consider some of the current available solutions and focusing on modeling and simulation, that is, you have the current existing systems are limited to rigid or on-road terrain, linearized kinematic models, and they're often non-optimal solutions and don't include vehicle dynamics and are mostly geared towards low speed. And for example, that's why there is a need actually for a solution which would for most extreme autonomous navigation on deformable terrains, as I mentioned, and at higher speeds. And, for example, for lower level steering and wheel velocity control, you can have a model-based model prediction control, and with that you can use linearized systems. But however, this becomes a challenge when you go for higher speed, and which is why we at the Tactical Mobility Research Group embark on this kind of work. I'd like to now zoom into our autonomous navigation project that we embarked on at Landwoods System, and this was through the thematic project that was initiated in 2015-16 financial year, along with in collaboration with other research groups across the CSIR. And that included both the Defense and Security Cluster, Next Gen, Enterprises and Institutions, which is formerly Miraka, Center for Robotics, which is formerly MEAS, and Material Sciences and Manufacturing, and which I will touch on in the following slides. The goal basically of our project was to demonstrate autonomous navigation of an unmanned ground system or vehicle, if you may, relying only on onboard sensors without GPS, RF beacons, and other external active identifiers. And the task would be plan a path. So we were aiming for full autonomy, and that speaks to level 5, if you remember back to the levels of autonomy. And that would be to plan a path between current position and end position, autonomously drive there to the endpoint destination, avoid both dynamic obstacles, and assess the terrain in situ as the vehicle is moving for trafficability. And as part of this, mapping was not part of the objectives. However, we were using a prior map in this case. And the project also supported several postgraduate studentships. The approach that we followed included where we identify problem identification and scenario analysis. And then we had an approach where we go to modeling and simulation environment of the actual environment, the vehicle in the environment, and the different components, and to hardware in the loop, testing the different system components within the loop. And the components included navigation, of course, perception, planning, control, and sensor fusion, and developing algorithms around that. Just a summary on the high-level outcomes of the project. These included capability establishment, infrastructure and tools, process development, and a hardware in the loop simulator, and a full-scale integrated development plan. And from these basically, and also being geared to be positioned for real-world impact. And from these, we aim to continue and hope to secure further funding. In the interest of time, I'll just touch on a few points from a technical point of view of what a system composed of, basically. And we approach this from a system architecture and communication framework point of view. We looked at this model-based system engineering approach, and that was obviously because of the advantages it presents for efficient communication, and so that to clear away any ambiguities, especially in a multidisciplinary group. And some of the benefits are listed there. And we also based our system, most importantly, and the emphasis was on the joint architecture for unmanned systems, which is a lot more applicable in the military context. But what it offers is a platform-independent, a modular system, which you can afford any, it works well as a research and development platform that you're able to isolate a subsystem and test it in isolation without necessarily upgrading other systems. With that, we had to consider how we go about doing a functional diagram, breaking down our system into functions and approach it that way. That included functional data flow, how we, across the different subsystems, we have the obstacle detector, we have the terrain classifier, the path planner, the driver systems, and the different components that go with. So how do we handle protocol, communication protocol between the subsystems within the bigger systems? The communication approach at subsystem level, whether we use at protocol, whether we use LAN, Wi-Fi, and so forth for the different components. And that focused a lot around the JSON format and applying a message server approach, which includes socket I/O. And the messaging was message synchronization, rather, using a waterfall model. I mentioned the JAWS architecture approach, and what that is, this is how the system was broken down. Basically, you have subsystem components, you have the path planner, what we call the driver system, which include the reflexive driver and proximity driver, and the vector knowledge system. And all these different components that constitute autonomy, you would have a dedicated ID. That way you can reuse the ID every time you want to communicate to each particular subsystem, and it's easier to identify it, and with that comes detecting of disconnections and so forth. The rest of the talk really is around the specifics that we zoomed into some of the techniques we approach around localization, and looking at localization, the approaches that we use, Monte Carlo and normalization, cross correlations, and the different approaches from the terrain traversability point of view, the dynamic obstacle detection, and some of the results there, and how we match all of that to generate a world map. And the path planner and the different approaches that we use there, like the modified A-star algorithm, and for real-time applications, and some of the results that we get out of that. And the reflexive driver, ultimately, which does, and primitive driver, low-level control of the vehicle. And to end off with this, the question remains, should we continue? Is SA ready to face autonomous vehicles? And with that, I'd like to end on a note with remarks that I would quote from our Transport Minister, Mr. Fikile Mbalula. This was in last year's conference, the Transport Conference in South Africa. And these were his concerns, that the pace is that we must not be relegated to catching up. We must be part of innovators. We must not only respond to what others have produced as dictates, because that will often give rise to additional challenges. The very fast pace and frequency at which new technologies emerge and their diffusion across the world leaves the question of whether South Africa is ready or whether it will be ever ready. Research and development funding has to be prioritized by the sector, especially government. And if you ask me, I'd say there is no time like the present. If there are any questions, ladies and gentlemen, we will attend to those now.